propose that we take a couple days on. Today we're getting into what is known as binomial distribution. So we're continuing to work with probability distributions. When it comes to probability distributions, you can have just general distributions, which is what we've worked with so far, essentially, where when you're dealing with just a general distribution, you need to know what all of the outcomes are and all of their probabilities are in order to really kind of get into knowing about those. But some distributions, such as binomial, you can know more about those distributions just by the fact that they are binomial. You could calculate different things other than just the probabilities, knowing that it fits this form. Now, when it comes to working with binomial distribution, one of the things they sometimes call it is they talk about it as being a binomial experiment. If it's something that you're actually doing things with, they ask if it could be put, or if it could be simplified down to a binomial experiment. To be simplified down to a binomial experiment, or to fit the idea of a binomial distribution, the first key thing is that first word, binomial. Generally speaking, bi as a prefix means what? 2. The key thing about what makes something a binomial distribution is it can be broken down into 2 outcomes. Now, the original setup does not have to have necessarily 2 outcomes, but it can be simplified down into 2 outcomes where you define one outcome as essentially a success and any other outcomes as essentially failures. The probability of success, or P of success, is always given by the variable of a lowercase p, and the probability of failure is then the probability of everything that's not a success. They give it by the variable q, but if the probability of getting a success is p, the probability of getting a failure is... Well, if the probability of getting success was 50%, what's the probability of failure? 50. The probability of success was 20%. What's the probability of failure? 80. Essentially, the 2 things have to add up to 100%, right? But generally, we don't deal with things in percentages. We deal with them in their decimal form. So, 100% minus the percentage is equivalent to 1 minus the decimal form. So Q is whatever 1 minus Q is. Now, again, the original situation can have more than 2 outcomes. As long as you can simplify it down to things that are success and things that are failure, then we're moving in the right direction. Even if I talk about something like rolling a die. If I want to talk about the probability of rolling a 6 on a die, I can break this down as binomial in the sense of there's 2 outcomes. In this, I just say that rolling a 6 is a success and rolling anything else is a failure. So P would be 1/6 and Q would be 5/6. There are a few other things that go with this, though. First off, there has to be a fixed number of trials. That's given by the variable n. What this means is that you have to have set up going into this knowing how many times you're actually going to do this experiment. In situations where you do things like best 3 out of 5, it is still required that you do all 5 trials, even if the first 3 are one by one person. You still have to continue to do all 5 because of that set number of trials. Otherwise, you're ignoring some of that probability of other situations happening. And that seems a little bit weird to some people, because how often when you play best 3 out of 5, the moment one person wins 3, do you stop? Yeah, oftentimes. If you do that, it doesn't fit binomial. Furthermore, each trial must be independent. What does it mean for things to be independent? One doesn't affect the other one. Something doesn't rely on something else. In probability, that means my ability to get a success does not change based on what has happened prior. Specifically, P is constant. If you have situations where you're talking about things like drawing cards out of a deck of cards, if you all of a sudden draw out a card and it's the ace of spades, and let's say you're looking for the probability of drawing a bunch of aces. So success would be drawing an ace, failure would be drawing anything else. You pull out that card, and if you don't put that card back, your probability of drawing an ace has now changed, which means P would not be constant. So if you want to think about that situation and you want it to be binomial, then after you draw that card, it must go back in the deck so that the number of cards in the deck has not changed. Otherwise, you've changed probabilities. So P must be constant in order to be binomial. Now the random variable x will represent the number of successes wanted. And the formula for the probability of a binomial distribution goes P of x is equal to. Now the formula itself might look something similar to a formula we had back in chapter 10. Back in chapter 10, I gave you this formula. It's the binomial theorem formula. Binomial theorem and binomial distribution are directly related to one another. Binomial distribution is probability application of binomial theorem. Binomial theorem, focusing on expanding a binomial, it put in the probability realm would essentially give us the sum of all possible outcomes of a binomial distribution. If I do binomial theorem, with probabilities being the things plugged in, it should always add up to 1 because it's giving all outcomes and adding up all of them. So they are directly related to one another, but we don't really use them interchangeably. Babe Ruth had a 0.432 batting average. Now, assuming I'm still alive, playing baseball. Let's imagine he has 3 at-bats. With that, we're going to answer the following. First up, if you have a 0.342 batting average, what does batting average actually measure? When you hit the ball. It's the likelihood that you get on base during an at-bat. Those of you who are baseball, softball, does that accurately represent that? I'm not a sports person. So just to be clear, it's the probability you're going to get up on base for an at-bat. So if you have 3 more at-bats in this situation, this is your individual probability for each time. I can ask questions like, how likely will it be for Babe to get 2 more hits? First off, I should double check. Is this binomial distribution? Can I break it down as a success or a failure? Yes, success getting a hit, failure being not getting a hit. Okay. Is my probability of success staying the same? Batting averages don't change that quickly, not to mention Babe Ruth's dead. To be blunt. Okay, is there a fixed number of trials? Yes. What is said number of trials? 3. 3 more at-bats means N is 3. Okay. P is probability of success, 0.342. What's that make Q? Everything else. 1 minus that, 0. Grab a calculator if you need one. Today's a calculator kind of day. Grab one if you need one. 0.658. What is x in this situation? What's our random variable? Two? Okay. So the probability of x being 2, which sometimes they write p of 2, sometimes they write p of x equals 2, and there's a reason they do that sometimes. I'm going to get in the habit of doing that because it's going to lead us into what we're doing tomorrow. Equals n combinations of x, 3 combinations of 2, times p 0.342 to the power of x, 2, times 0.658, that's q to the power of n minus x. In other words, 3 minus 2. The way the binomial probability works, the n combinations of 2 gives me all of the different combinations, all of the different ways that we can get 2 hits. It essentially breaks down, okay, we could go hit, or success, success, fail. We could go success, fail, success. We could go fail, success, success. Ugh, I can words. This essentially gives us all the orders. Then it's the probability to the power of the number of times we want to succeed. And then the probability of failure essentially goes to the number of failures that would mean you'd have to have. In order to have 3 at-bats, 2 successes, 1 has to be a failure. Hence, that ends up being a 1. Y'all remember how to get to the combinations in your calculator? Start by putting the 3 in first. On the TIs, you go to math. Scroll over to the probability menu, and it's the third option. On the Casios, you put the 3 in first. It's under option. Scroll over using F6 until you find the probability menu, and it's F3. When you type this into your calculator, make sure that you do that before putting in the calculator. Unless you really want to put parentheses around it to make the calculator do the correct math. Y'all can do math. It's 3 minus 2. On probability, how many decimal places have I been wanting if it's not a fraction? 4 decimal places. Or if you change it into a percentage, that's 2 decimal places. Either way, you're giving me the exact same numbers. So, 23.09% chance. We could create relative frequency tables still. That piece hasn't gone away. A relative frequency table is a table that gives you all possible outcomes and all of their possible probabilities. If X is a number of hits, what are all my possibilities in 3 at-bats? 0, 1, 2, 3. and I can find each of those probabilities. To find each of those probabilities, I would use that probability formula for each one. N stays 3, P stays 0.342, Q stays 0.658. Those things have not changed. The only thing that's changing is X. For 0 hits, X is 0. So 3 combinations of 0 times 0.342 to the power of 0 times 0.658 to the power of 3 minus 0, also known as 3. Now, if you do enough of these, or if you look a little bit closer, you actually can shorten the amount of things you type into your calculator. A couple of different ways. One way is, if you've already gotten it typed into your calculator, remember, you can edit previous things you've typed in. On the TI, click second and enter. It brings that back up, and I can just go through and change just the specific numbers I need. On the Casio, my Casio's yelling at me right now. Now, I didn't put the entire thing in my Casio, but if I scroll either up or left, depending upon the Casio, it'll let me do the same thing. That's one way to shorten down what I do. Or, you do enough of these, you're also going to learn something about easy ways to shorten this. Some of them you should already know. For example, what's anything to the power of 0? 1. Do I really need to type in times 1 into my calculator? No. What's anything combinations of 0? Also 1. We proved that back in chapter 10. Remember Pascal's triangle, the first number was always 1, going down that diagonal. Same with n combinations of n, so 3 combinations of 3 is also going to be 1. It's, in fact, on this one, I could have just as easily typed in 0.658 to the power of 3 and to the power of 3 and gotten the exact same answer. Do you have to do that? Absolutely not. Use the formula. But you get used to using this formula enough, there's going to be times where you could shorten it down. For 1 hit, now I'm changing X to 1. That becomes 1, that becomes 1, and 3 minus 1 is now 2. If you know your combinations well enough, you would also be able to shorten this down and know anything a combination of 1 is always the number before it. We also proved that back in chapter 10. But you don't have to memorize that. You could just go through and change these numbers. I already did 2 in part 1. What should all of these add up to? 1. Even if you're rounding, if you round all of them the exact same way, they should still always add up to 1. you can ask the question, how many can you expect for Ruth to get? Now, expected value, we learned of a way to do it last week. Outcome times probability plus outcome times probability plus outcome times probability plus outcome times probability. And that will still work. But binomial distribution has a shortcut. Because of the fact that there's only two outcomes in the situation, and that the probabilities do not change from trial to trial to trial, you can find this a different way. First off, expected value. Oftentimes given by E of x, but it is a weighted mean, and so it's often given by another variable that's associated with mean, which is mu. That's a variable mu. It's a Greek letter, looks like a lowercase u with a tail coming off the front of it. It's mu. It's given by a real simple formula, NP. So, in this case, N is the number of trials, 3. P is the probability of success, 0.342. Multiply those together. I get 1.026. Now, technically, that was a number of hits, and in the real world, if someone asked you how many hits would you expect, would you answer them with 1.026, or would you just tell them about 1? You'd probably say about 1. I'm running myself out of room. You might also be asked about standard deviation. Now, this is a probability distribution, which means we can make that big old chart. X, P of X, X minus E of X, X minus E of X squared, X minus E of X squared times P of X, find the sum, take the square root. Or, there's also a shortcut for binomial. Standard deviation is given by sigma. And it's the square root of NPQ. N is 3. P is 0.34. Now, we already did that multiplication, so in all technicality, there is an additional formula for sigma, and it's the square root of mu q. But you don't have to do that. It's just as easy to do this one. It's 0.8216. If, I don't have a TI-83 over there yet. If you're typing this into your calculator as written, particularly on the, actually it's the Casio that we need to worry about, not the TI. What am I thinking? Particularly On a Casio, if you do square root of 3 times 0.342 times, type it incorrectly, 0.658, it's going to give you something different because your calculator is going to determine this as the square root of 3 getting multiplied by these decimals. So make sure you got parentheses going on. So far, nothing too scary. Binomial distribution is fairly straightforward. I've got one more example. It's got some parts to it, but as we get further and further into this chapter, one of the questions you're going to have to be asking yourself when it comes to problems that are probability is, can it be broken down as a binomial experiment at all? Because we're going to get different types of probabilities that can't be broken down as binomial. Binomial has 3 main requirements. First requirement is its 2 possible outcomes that you can define as success or failure. Brody, does it have 2 outcomes? What would be considered a success? And what would be considered a failure? Yeah, you got win versus lose. Or you could argue win versus lose and tie, but either way, you've got a win percentage and then you've got everything else. Another thing that is required is a fixed number of trials. Vivian, is there a fixed number of trials?
Yeah.
How do you know that?
It says in the top.
What does it say?
5?
There are 5 games. That's telling you the number of trials. That's telling you it's fixed. The third requirement is the probability of getting a success is not going to change throughout it. P is constant. Julia, is P constant? Yes, how do you know it? P is the probability of success. What's the probability of success? 65%. And it says that it's true for any particular game. In other words, it doesn't matter who their opponent is. Oftentimes when they calculate your likelihood of winning a game, they compare it to, well, who you're playing against. Because to not look at that in the real world would be naive. We can have the absolute best basketball team in the entire high school league. But if you put us up against the Timberwolves, that doesn't mean our probability of winning the game is the same. So, you have to pay attention to that. But for this one, that's why it says for any particular game, is it's ignoring the fact that it could vary depending upon who your opponent is, etc. So yes, P is constant. There's two outcomes. Fixed trials. Those are the three requirements. What is the probability of winning exactly 3 games? Okay. In order to do this, I need N, I need X, I need P, I need Q. Those are my 4 variables going into this. Bella, could you give me any of those 4 variables?
Is X3.
Yep. Beautiful. Quinn, could you give me any of the others? P is 0.65. Harmony, could you give me either N or Q? N is 5. Caleb, what's Q?
0.35.
How'd you get it?
1 minus 0.65.
Correct. That's the only one you actually have to do a little bit of calculations on. That's why I asked for the clarification. So I plug into my formula. That formula. Probability of X being equal to 3 equals 5 combinations of 3 times 0.65 to the power of 3 times 0.35 to the power of N minus X. 5 minus 3 is 2. I'll give you a minute to type it in. I've already got a name pulled of who I'm going to ask. Emily, what did you end up with? 0.3364. Also known as 33.64%. I don't care which form you give it to me in, but if you're going to give me the percentage, put the percent symbol. Okay. How many games can we expect the team is going to win? Austin, when the question is this, what am I actually calculating? What's it asking me to find?
Probability.
That's the keyword. Expect. I'm looking for expected value, also known as probability mean. Isabel, what's the variable for probability mean? Mu. You could argue it's E of X as well, but generally it's mu. What's the formula for mu? For binomial? N times B. N was 5, P was 0.65. We get 3.25. In layman's terms, you would probably say about 3 games. If you just tell me 3.25, I'm good with that as well. If you tell me the about 3, then please show me your calculation as well. Don't just write about 3 and move on. Now, if I want a mean, I also want to figure out how likely it is to vary from that mean, which is where standard deviation comes in. Standard deviation is given by the variable sigma, and what's the formula for it if it's binomial?
The square root of n times b times q.
Square root of n b q. N was 3, p was 0.65, and q was 0.35. Type it into my calculator. Make sure I have parentheses, particularly if I have a Casio. And Marissa, what do we get? Oh, yeah, N is 5, isn't it? Don't mind me. 1.0665. So you can expect to win about 3 games with a variation of about a game is essentially what this is going to be down to. Okay, overall, binomial, nothing too scary. Even with the second example. We are on page 790. No, we are not. Let's try this again. You're on page 756. I can write the page number properly, I swear. Numbers 7 through 9, 14 through 21, and then 25 through 27.